Welcome for this second lecture. It will be less general than yesterday, but I try to make things quite easy. So if I'm going too fast, just stop me. If you have questions, just ask me. Okay? So today we will talk about polynomials and Galois extension and finite fields. I just forget the name. But first, polynomials. So in Paris GP, you have several ways to define polynomials. You can define it by the explicit expression like here. Be careful here, the polynomial is P, not P of X. If you write P of X, you are defining a function. So it's not the same object, it's not the same type. So you can define it with the explicit expression. You can also define by summing terms. So I'll have a look to this function sum, which will do that. You can also define it with giving a sequence of its coefficients. So here V is storing all the coefficients of P, and after that with the function pol with a capital P, you can get this polynomial. So this one is the coefficient of the leading term here. And this is the constant one. If you want it in the other way, you can use Polynomial, which reverts to polynomial. So here the leading term is 4. But you can also, if you have any kind of polynomial, you can reverse it using polynomial. And here I show you that this is the same thing to reverse this polynomial with this function or to use polynomial. So yeah, when you're dealing with polynomials, sometimes you want to know more about the roots of the polynomial. You have a function for roots, which gives you some approximations of the roots. You can define the precision. We talked about that yesterday. You can do more or less, but it will give you each time floating points in C. So sometimes we need a polynomial with a specific approximate root. You can do that with algebraic dependence. You give it a root, then a bound on the degree, and it will give you a polynomial. And one of the roots of this polynomial is an approximation of that. You can also use interpolation, like Lagrange interpolation. You specify a list of values, and then the list of the images, and it will give you a polynomial for which here P of 1 is 4, P of 2 is 0, and P of 3 is 2. Okay, so you can specify how many values that you want. Of course, the degree of the polynomial will increase. And you can also define a polynomial, like a monic polynomial, by giving the roots, if your roots are integer. So here, A is still this vector. So here I ask for a polynomial with roots 1, 2, and 3. So it's x minus 1 times x minus 2 times x minus 3. And you can use also some functions to generate a very famous polynomial. Hermite, Daguerre, Legendre, Chebyshev, and so on. You have several functions. If you need it, you will find everything in the documentation. So we spoke about polynomials in one variable. Sometimes you need more than one variable. You can do that, but remember that there is always a main variable. And if you do not specify anything, the sequence is here. X is your main variable, then you have Y, then Z, then W, then U, and then D. So here, this polynomial, if I ask for the coefficient of f of degree 1, it will take the coefficient of degree 1 in x. So here it's y. If I ask for the degree of the polynomial, it will give me the degree in x, which is p. And if I ask for the leading term, same thing, leading term in x. So this is the coefficient of the maximum degree. If you want to have some information for another variable, you just specify in each of the functions, you specify the name of the variable in y. So the term of degree 1 in y is x plus 4. Your polynomial, we saw yesterday that if you do not specify anything, the software will decide itself in which domain all the operation will be done. You can use factor to factorize a polynomial. We like factorization because it makes things quite easy. If you do not specify anything, factorization is made over Q or Z, the default space. So here, these two lines, So here, this polynomial is a product of two terms of degree 2 and 3. So here, when you ask for factor, you have one line per factor, and each time you are the polynomial and the exponent. You can also ask if your polynomial is irreducible. For example, this one is irreducible. And if you ask to factorize an irreducible polynomial, of course, it does not.
Polynomial is saying reducible over this field, we have to specify.
If you do not specify anything, it's over Q or Z.
How to change the field? If you want to see reducible over R or C, then.
Oh, you will see that in the exercise sheet. I don't have so much time, so I cannot explain everything, but there is a special exercise for learning how to specify it. You can also want to use periodic numbers. In that case, I just missed a slide. No. Okay, so it's always the same polynomial. It's called this one. This one is irreducible over Q, but it's not over some QP. If you ask for the discriminant of this polynomial, you see that this discriminant has two different factors, 2 and 3. So if we try to factorize it over Q3, we have something irreducible. Over Q2, it will be irreducible also, but over any other QP, you can factorize it. For example, over Q5, you get two different factors. So it's not irreducible anymore. So factor periodic allows you to factor. Here, it's your periodic precision. If the big O at the end. And sometimes we want to work on finite field. So if you want to factorize over FP, you have a function called factor mod to factorize this polynomial modulo 2, 5, for example. So mod 2 is irreducible. It's x over 4. Mod 5 is not irreducible anymore. It's the product of two polynomials, x squared plus x plus 1 and x squared minus x plus 1. If this is difficult to read, you can lift it to have an expression easy to read in. But keep in mind that here, mod 4 is the same thing as mod minus 1. So when you have this, just be careful. With polynomial, we may want to define some number fields because you know that number fields are obtained by quotients of Q of T, quotient by a certain polynomial f, with f irreducible, and we denote by alpha, one of the roots of f, such that k is in fact Q of alpha. So you can factorize a polynomial over a number field using factor n. Here I try to factor this one, mod t to the square plus 1. So here it's to the square plus 1 is my f. So you're going to that, and you can lift it again. And it permits, for example, here, to show that in Q of I, this polynomial is the product of these two ones. Okay, here this is Q of I. So to basic computation in number field, just keep in mind that if you are in a number field, you are in fact in a mod thing. You are mod some polynomial. So you can do everything after that with polynomial types. Okay, you can make some products, you can add, you can factorize, you can do a lot of things. So for example, if I define this dichotomic polynomial, this is another way to define polynomial. I talked about like very famous polynomials, dichotomic ones are. So if we take this dichotomic polynomial, we can compute its fifth power quite easily, and it's I would suggest that you put the power of 5 after the mod, so that it computes with some simplification each time, and it's quite faster than to compute the power of 5 of your polynomial and then to compute the modulus. So here we get that alpha to the 5 can be written like that. Yeah, with x, but this polynomial defines the field Q of alpha. So x has the same rules than alpha. And we can check that the roots of this polynomial are roots of unity by computing the power 15. We get -1, that means that the power 30 will be 1. And you can always lift it to have some easy to read form. And when you define a number field, so you have your polynomial, you define your number field, sometimes it can be quite useful to have a better polynomial to define the same extension. For that, you can use Polynomials, which try to reduce your polynomial to a best one, best in sense of the degree and the size of the coefficient. So here, if we take this polynomial, it will define the same number field than this one. I'm sure that you agree that it's better to work with that one. And these two number fields are isomorphic. So once you know how to define extensions, number field extensions of Q, you may want to look at Galois groups. So in biology, you have a lot of, not a lot, but quite many functions around Galois groups, but only for Galois groups over Q or an extension of Q. We don't have anything for finite fields, but in finite fields, you know that the Galois groups are cyclic, generated by Frobenius. So in fact, you don't need anything to compute it. So you consider a number field k defined by a polynomial that I will call f. So k is q over f, q of x over f. You can ask for the Galois group of the splitting field of f of x using Galois. So if your extension is a Galois extension, it will give you your Galois group of k over q. But if your field k is not Galois, then it will give you the Galois group of the splitting field. So here, for example, I have a polynomial of degree 6. So I define an extension of degree 6. And the Galois group is of order 48. So it's quite larger. That means that this field, the field defined by T, is not Galois. And here you have the order of the Galois group, but also its name. So it's not quite easy to read, but you have some functions that translate you in a language that you know. So this is the structure of the Galois group, and this is the order. If your extension is Galois, then you will have the same order than the degree of your polynomial. And for example, this one is z over 4 times z over 2. And this one, so this expression here, means z over 2 times s4, which is actually a degree of order 40. What is it? This is the sixth. I cannot pronounce this word, but well, you have a list of all the group of order 6 of order 48, and this is the 6. Like, no. It's just you have a list with several items, and this is the items.
It's some database.
It's a kind, yeah. It's in a gap for database. I will work after. Gap for. Yeah. So well, you have some function in PyGP to translate these names into something that you may understand.
This is just coming from gap, right?
These names, yeah. So once you know that your extension is or not Galois, you may want to do some computation with its group. For that, you need to use Galois init. You will see other function blah 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 in it to initialize a structure. So here you're initializing the Galois group of P. In that function, in the output, you have a lot of information. You have 8 items. We'll see that in the next slide. And it contains a lot of information on the group. If your polynomial defines a non-Galois extension, then you have the same function but for splitting field. These two functions are different so that you cannot forget that your extension is not Galois. Yeah, it's to avoid some confusion. So here, for example, Gal2 is the Galois group of the splitting field. And you can always get the polynomial that initializes the extension. So here I check that the degree of this polynomial is 48. The polynomial we had before. So what can we find inside the Galois init of P? You check. I put here a semicolon because the output is quite huge. You can find your defining polynomial. This one. You can also have the roots. These are periodic roots of this polynomial, which are given by integers, quite big, in Gal mode. So modulo some prime, which is this prime, have a look at the documentation if you really need to work with this root. But you can have an access to the root. You can also find the Galois group of your extensions, which is given by a vector of permutations of roots. Something quite natural, Galois groups are a matter of permutation of roots. So you have your permutation of roots here, which is identity. So you have a list of all your permutations. And you can also have generating subsets of your group, which will be expressed with permutation of the roots also. So here, we saw that this Galois group is the direct product between two cyclic groups. One is generated by this permutation, the other one is generated by this permutation.
The permutation is given in one time.
Yeah, that means that 3 is going to 1, 1 is going to 5,
It's cycle.
it's cycle. You have other information. I will look at the documentation if you really need something. I cannot explain everything. These were some shortcuts. .for, .mod, and so on are shortcuts to some part of the output. You can, once you have a Galois output, so you store the structure of your group, and with this structure, you can do something else as, for example, have the list of all the subgroups. If you wanna have, I don't know the English for that in French, is treillis des subgroups. When you want to grow, you have your big group and all the subgroups.
Like tree.
Three, if you want. This is not exactly a tree because you have a common root and you have a common sky and everything.
The whole set of the also diagram.
Yeah. Diagram of all subgroups.
So this is completely gapped.
It's based on gap, yeah. So you can have the list of all your subgroups. Here the list is called L. And with every subgroup, it has a structure of groups, so you can check whether it's abelian. So for example, I see that all my subgroups are abelian. You can also have their name in GAP4 small group database. So here it's the second group of order 8, the first group of order 4, so this one is the cyclic. Second group of order 4, this one should be the direct product of two cyclic, Z over 4, Z over 2, Z over 2, Z over 2, and this one. And if you have a group in that kind of writing, you can ask Galois get name AB, here A will be 4, B will be 2, and it will give you a most readable name. So here, I tried with this one. Second group of order 8 is C4 times C2. For one here,
First group of
first group of order 4, it's the
what is the second one?
This is another one. These two ones are not generated by the same polynomial.
This is the
here we have a lot of subgroups. We have 2, 4,
that's a list of
6, 8. So we have here a list of 8 subgroups. And for each of these subgroups, I ask if it's abelian. They are all abelian. And then I ask who they are. And the first one is 8, 2, the second one is 8, 1, 4, 1, and so on. So you have the list of all the subgroups with different polynomials that generate them. And with that, you can ask for all the subfields, the Galois subfield of your extension. So you can compute Galois fixed field fixed by some subgroup. So here you have to give your Galois group, I mean the big one, and one subgroup. So here, I don't know if you remember in the previous slide, the first of them was the entire group. So if I ask for the fixed field of Gal fixed by itself, I should have Q. So let's have a look. Here. We have Q, it's something like 0. If I want the fixed field by Z over, it was the first Z over 1, I asked it, and it says me that it's generated by this polynomial.
Do I have to install some extra library for this? Because I'm saying
If you are on Linux, yes, you should download PolGal. Galdata, I guess. You can find it in the documentation how to install Variation. If you are a Windows or Mac user, it should be included in the binary. So here I can compute one by one every field. And if I want all the subfields of case, I can ask for Galois subfield of my Galois group. And here, subfield, the first component of the output is the polynomials that's generated. So the first one is generated by X, so it's Q. This one. The second one is generated by this polynomial, but I get Q. And you have all the other ones. And the last one is generated by your defining polynomial. So it's the total extension that you have. So you can easily get all the subgroups of your Galois group and also all the fixed fields, so all the Galois subfields. So we spoke about polynomials, we spoke about Galois theory. You will notice if you have a look at the exercise sheet, I put other functions inside exercises, like, for example, functions about the characters of your Galois group, if you need to study some representation. So you have other functions. I put in the slide only the main one, but you can find more in the detail. So in finite fields, we can also do the same than for a number field. Just consider that it's Q over something, over some prime here. So here I take some random prime. Yeah, you see, random prime. I will take some random prime less than 2 to the power of 100. So it's huge. You don't want to do the computation by yourself, so Validity will do that for you. A will be 2 mod VP. And here, when I write that, A is not an integer anymore, it's an integer mod. If at some point you have a function that doesn't work well, it could be interesting to use the type function just to be sure that you're using the good object. Here, A will be an integer mod P. If you want to check if your mod's a good P, you can ask for A.mod. It says that A is an integer mod P. You can check that this identity is verified. It should be 1. So compute it. It's 1 mod P. And same thing than earlier. If you don't want this to be printed, just temporarily to have a quick vision of what you are doing, you can lift it to this. Sometimes you may, I think I did not write it in the exercises, but you can use also center. It's the same thing. You have two different functions with different names, but basically they are the same. And if you want to define a finite field with a non-prime number of elements, you may have to compute the quotients by a polynomial. You know, if you want f9, you have to take f3 of x and to quotient by a polynomial of degree 2. This is what I will do here. So let's take t, this polynomial of degree 2, and have a look at b, which is x plus a mod t. Remember that a is 2 mod p. So finally, this thing is x plus 2 mod p mod t. Okay? If you have some type of b, it's a polynomial. It's a polynomial mod something. And all the coefficients of this polynomial are mod p integer. You can always recover the polynomial that you use at the beginning by p.com. Here it's 1x plus 2. So your polynomial is x plus 2. And you can ask for the mod polynomial with b.1. It's a polynomial mod. So here, polymod means a polynomial mod a polynomial. Okay? So we have not a finite field structure in ParisGP because finite field can be just defined by giving all the elements. This is what we are doing. For example, if I define C as being a generator of the finite field of order 3 to the power of 8. Here you put a quote C saying that the polynomial which defines your finite field, I mean this polynomial field, well, here we are on FP of something over a polynomial, and here I say that I want my polynomial to be in the variable C. You should always do that with a variable quite weak, so that if you are after computing some polynomial, you will not have any transfer. I mean, your polynomial should have, if from the beginning, if you want to consider polynomial with coefficients in a finite field, the variable of this polynomial has to be stronger than the variables that we use to define the finite field. This is why I use C, because C is weak. Remember X, Y, Z, and so on. C is really weak. So here, C is a generator of this field. If I ask what type of C, it's a finite field element. So f of gen, finite field generator. Once you define your element like that, it's an element in a finite field. I can ask for the characteristic of your field, your field. You can also ask for the polynomial which define your finite field. And this polynomial will be lifted to Z so that you can easily read. Here, C is your generator. You can check that this polynomial is irreducible. And here, it is a hint. By multiplying by 1 mod 3, I say, well, the coefficient of my polynomial are integer mod 3. Okay, so you were asking how can I just specify the domain when I want to factorize something? This is like that. You just multiply by 1 mod something. So here, this polynomial is irreducible mod 3. And it's of degree 8 over F3. So F is for the degree, mod is for the polynomial, and so on. So here, I define a new function field element, which is B, defined by C to 9 plus 1. B is given by this polynomial in C, where C is the generator of your finite field. You can at any moment get this expression by asking for this is a polynomial associated to B. And this polynomial is just a polynomial. It's not in finite field anymore. It's not a mod something stuff. It's just a polynomial like with coefficients in Z. Okay. So sometimes you may want to define by yourself your finite field by giving the polynomial. Sometimes you just want a finite field with, for example, here, 3 to the power of 5 elements. So you just ask that, and it will give you back your polynomial. So you can want to do the converse. I mean, you can want to choose your polynomial and define the finite field which goes real with, and you can do that also. So with ff init, you get a polynomial. With ffgen, you get a generator of the finite field polynomial. Just be careful here. Your polynomial must have coefficients in Z mod PZ. So either you write the last coefficient with the mod stuff, or you write your polynomial and at the end you multiply everything by 1 mod P. Okay? And in finite field, you can use a lot of quite usually functions. You can ask for an element. C is our generator. It's an element of the finite field. You can add a constant. You can multiply by the constant. You can ask just for some constant. You can compute the opposite. I'm using English for that. Yeah, you can put it to the power of -1. You can also get a random element of your field by asking random C, where C is the generator. Okay, if C is the generator of finite fields, this will give you a random element in your finite field, given by a polynomial in C. You can ask if something is a square or not. So D, remember, it was C to 9 plus 1. It's a square. You can ask for the trace of an element. You can ask for the norm also. You can ask for a minimum polynomial. Given as a polynomial with coefficients in F3. Yeah, because we are in F. 3 to the power of something 5, I guess. So everything works well, but you have to be really careful to use a generator each time. Because in fact, this generator that says the software, well, I am working with finite field. And the last slide before you can maybe do some exercises. When you want to the factorization of a polynomial in a finite field, just give your polynomial with a generator somewhere, and factor will work. We don't have any FF factor function because it works really well like that. So here, this polynomial of degree 5 is the product of 3 polynomials of degree 1, 2, and 2. And each polynomial will have coefficients expressed with according to C. And you can also ask for roots of your polynomial, and the same thing, roots will be given as polynomial in C, your generator. So with that, you should be able to do almost whatever you want in finite. Okay? So I will stop here for all this information. You can get the slide on the webpage. You can also get the exercise sheets on the webpage. And if you want to do again everything that every function that are in the slide are also in the text file available on the webpage, so that you can just copy paste to be faster. Well, thank you. Let's do some exercises. And if you have, yesterday some of you asked me how to write outputs in the file on your computer. So if you just download again the exercise sheet of yesterday, I added some paragraph on it. So how to write the file.